recording. Try to mute all. There we are. All right, so this is lecture 11, and we are going to finish the discussing of chapter 6 by this lecture, and this will also mark the coverage of our coming exam 2 on next Tuesday. So the exam 2 coverage will be, as I mentioned in the email, from chapter 4, 5, and 6. So in terms of the lectures, will be covered up to this lecture, lecture 11. Again, we will have 3 problems for this coming exam, and we plan to start the exam 9 in the morning till 10:45 for the exam, and I leave 15 minutes for you to convert the PDF file and upload that to Canvas. Any question about the exam? Any general question? No? Then let's move forward. I do want to mention that we will have the office hour this afternoon and during the weekend on both Saturday and Sundays I shall be available online. So if you have any question, feel free to log in and have a chat with me. So in terms of the lecture material, we were talking about the residual properties.
What time are you on call on weekends?
I'm sorry, I did not
What
get.
time are you on Zoom on weekends?
Check my email.
Okay.
I mentioned that in the email. So we were talking about the residual property, but before that, we also had some math last Tuesday. So we were basically talking about all those energy equations. If you think about the energy equations, now we have 4. Starting with the internal energy, U would be Q plus W. We have the entropy would be U plus PV. We have Helmholtz energy would be U minus Ts. We have Gibbs energy, which is H minus Ts. So that is the 4 energy equations. Then we move on to talk about the 4 derivative. I will just use one example over here. du would be TdS minus PdV. So this is the 4 derivative. So with that 4 derivative, we realize this is U is a function of entropy and volume over there. And then we also realize that we can take advantage of the second order derivative. So this is with respect to S and V. So we are going to have dt over dv while keeping the entropy fixed, shall be the same as d minus p over ds while keeping the volume fixed. So try to take a look at those 4 energy equations and try to figure out if you are comfortable with all those equations or not. And the use of those would be, now we are able to convert the entropy involving terms, and we can convert that into PVT terms. So right after that, we were also talking about the math where we try to put together the request. H would be the function of TP, or entropy is the function of temperature and pressure, how we can derive the general working equations, working functions for the enthalpy and entropy. We did not move on to talk about Helmholtz energy or Gibbs energy. I hope you realize that it's once we have this enthalpy and entropy, for example, G, the Gibbs energy is simply H minus Ts, right? If we just combine, now if we have the working function for enthalpy and entropy. Temperature is the state parameter, so we can simply combine the two equations to receive the working function for the Gibbs energy. So this is why we're only talking about the enthalpy and entropy in our lecture on Tuesday. And we were also talking about the residual property, which is for any property of interest. The residual property is defined as the uh, property at that temperature and pressure minus the imaginary ideal gas behavior. This is ideal gas. We assume at that temperature and pressure, we are still having the ideal gas behavior. Keep in mind the temperature pressure should be the same, and we try to evaluate what would be the difference. So if you think about the where this request is coming from, we have the sort of the diagram. So if I have the ideal gas, and of course for the ideal gas, I have to put T naught and P naught. Usually P naught is small, right? So it's quite close to 1 bar. It's actually required by the standard state IUPAC definition. Then we try to see if this is moving. What's going on? If this is moving to the real gas, now the real gas is at temperature T and P instead of T naught and P naught, and we try to look at those property change. We can take a look at delta H, delta S, and if we have all those, then it should be really straightforward for us to receive delta G, delta A, and so on. So this is why we typically pick up that two quantity to illustrate the calculation. So now we try to design the path, right? We try to so here we are having temperature and pressure are changing. We try to pick up a one at a time. So the first change would be, now we try to go from this ideal gas. We try to remain the ideal gas by keeping the pressure. So this is still the true ideal gas. If we simply change the temperature from T naught to T, but maintaining the same low pressure, so that's a true ideal gas. Along that path, that should be the isobaric change. Now we try to move the pressure while keeping the temperature fixed. Keep it in mind that we are keeping the temperature fixed along this path. So this is the isothermal process. And over here, we would have this direct movement to the final state. But then we come up with the idea that we try to evaluate moving from P naught to P, how terribly the system is deviating from the ideal gas assumption. So this is why we try to insert another imaginary state, and we assume this is still ideal gas. And this is at T and P, right? So again, pay the attention to the temperature. Temperature is not changing. It's basically the pressure change along the path, the isothermal process. So over there, we try to now evaluate what is the difference between the imaginary ideal gas state to the real gas state at this temperature Tp. So this change is the so-called residual property change. All right. So this is the diagram we had from last lecture. We look at the property change of the final and the initial. We try to design the loop, the path to calculate the change. Then this delta H would be simply is H minus H naught star. So this is H naught store at the ideal gas condition, then we can have this H P naught, which is the isobaric, keeping the pressure fixed, simply changing the temperature, and we have this delta H temperature, where we are going to keep the temperature as a fixed value for the isothermal process, and then we are going to have this HR, right? So if you manipulate the term, then we are going to have the corresponding two terms over here for both enthalpy and entropy. And then we had a look at the turn, and we try to say this is a fixed temperature process. I had a question last lecture. Why we are only interested in the fixed temperature process? Any answer on this question? Why having the definition of residual property, then we go ahead and try to write down this term, keeping temperature fixed. Anyone has any thought on this? Why not fix the pressure instead of temperature?
Is it because real gases at low to moderate pressure still behave like ideal gases?
Not really. That's not the reasoning. So if we go back to this diagram, or maybe the one I just had, try to pay attention to the bottom three states. From the ideal gas over here to the imaginary ideal gas to the final real gas of interest, you can see that the temperature is always fixed, right? So here we just evaluating if I'm changing P naught from some other pressure P, what would be the deviation to the ideal gas assumption? So that means the residual property itself is defined along the isothermal process where temperature is fixed. So we are only probing changing the pressure a little bit or changing the pressure significant value and try to look at the deviation from ideal gas to the real gas state of the final. So that is why the residual property itself is following this isothermal process. So this is why when we evaluate the residual property, we have to keep the temperature fixed. So that is from the definition, nothing special. So does that make sense?
Yes.
Cool. So now if we are happy with that, this is actually quite important yet sort of interesting understanding why we all of a sudden move on to the fixed temperature process. I hope now you see that is because the definition itself is from the isothermal process. You try to evaluate what would be the damage by changing the pressure, how we are going to manipulate the ideal gas behavior to real gas. So if this is the case, then we are able to move on. We try to evaluate the any residual property as a function of pressure, and we try to set up the partial derivative. Once we have that set up, then we can take the integration. We can move from the low pressure to high pressure of interest, and we can check the residual property change or the residual property itself. So this is the first question I have. Or I also had a question on the highlighted last line. So if we follow this equation, then we sort of combine the two terms. This is indeed, this is the delta MR, which is the MR of final, MR of the initial. So not this 0 stands for the initial state. And then when we combine the other two terms, then we just take the integral from the initial pressure to the final pressure, nothing special yet. But here we have this conclusion. When P naught goes 0, we are going to have this initial H of R is 0, S of R is 0, VR at this very low pressure, 0 pressure is not 0. Anybody had any thought on those three values? Do they make sense or not really?
I'm confused.
Where is your confusion?
Me too. I don't know why there's 0.
So
Aren't they only dependent on pressure? So if pressure goes to 0, then the values go to 0?
sort of, but not exactly. But this is because when we have this dp term, right, we have to look at the P naught and the P. So here we are simply confining this P naught. So this argument is a little bit strange. Let me try to explain to you a little bit more. So here we try to say this is the ideal gas. This is the initial ideal gas. And now we are going to push this ideal gas to the pressure goes to 0, right? So let's say we are going to have the ideal gas. We are going to have this further pushed ideal gas behavior. This is 0 pressure. This is still super tiny pressure, P naught prime, which is a small change to the 0 condition. So if that is the case, then we are able to use both P naught is close to 0, P is also very close to 0, then the change of the process would be the value of itself. Because we need to somehow manipulate and create this residue, this H of R. Right. So basically we are trying to split this P equals 0 state, and we try to look at the change to slightly increase the pressure, but that pressure is still very close to 0. So if this is the case, then this delta HR near 0 pressure will be the value of the HR at 0 pressure. Okay. So for the entropy and enthalpy at this 0 pressure or quite close to the 0 pressure, they are all behaving like ideal gas. So if this is ideal gas, if we go back to the previous two equations we derived, H as T and P, S as T and P, we could have the two values should be 0 when we approaching P goes to 0 for a very small change over there. But the volume is a little bit different. This is because ideal gas PV over RT, then V is RT over P. When we are having this P goes to 0 over there, then we are going to have the volume as infinity. So what you are going to have is you are going to have this VR over naught UR sort of having this as infinity minus infinity. So that shall not guarantee a zero to you. So that is why it's a little bit confusing, but we need to accept that we are not, we are at this zero pressure is not zero. We cannot guarantee that. Okay. So this is purely coming out of the math analysis. I cannot find a better way to explain that. I think in the textbook, the book just provides us that statement. At the zero pressure, the residual property of enthalpy and entropy would be zero, but not the volume. So I was trying to have some explanation. I hope it's helpful. Not really know whether you are happy to accept the analysis or not. Okay. So let's move on to the calculations we had. I want to revisit so that you feel happier about the whole process. So in general, the V of R, the residual property of volume, when we just had the analysis, it was a bit confusing, but when it comes to the actual calculation, it's the most straightforward calculation for residual property. So basically, you just need to get the real value of Tp. You need to evaluate the value of volume at ideal gas behavior of Tp, so that you use PV over RT to receive the volume RT over P, and take the difference. That shall be your residual property. For the enthalpy and the entropy, or the Gibbs energy, Helmholtz energy residual property, it is a little bit complicated. So if we start with the definition of itself, and we agreed that residual property is indeed from the isothermal process, so the temperature change shall be always zero for any residual property calculation. So that is zero for any residual property. Then we take the partial derivative with respect to pressure. So on both sides, we take the partial derivative, and over here we have this ideal gas behavior. Please see the slides from last lecture. I showed you why this term is zero, why the enthalpy of ideal gas does not depend on pressure. So this term is zero. Please refer to the previous slide for this term. And then this is simply dH over dP at fixed temperature. And the fourth derivative of enthalpy was derived from last lecture. So here dt term, that one is zero because it's the fixed temperature isothermal process. Then this goes to V minus T dV over dt P dP. Right, we are only having the second term left to evaluate the enthalpy dependence on pressure. So this is how we convert for the residual property. We are using the fourth derivative of enthalpy, and we come up with this term. Then you just need to evaluate from P naught to P, or in the your working equation, we try to push the P naught to zero. Then you can see that this is HR of interest of pressure minus HR initial, right? Initial at P goes zero. and we just had the analysis. This goes to 0 at 0 pressure. So this is why now if you reorganize this a little bit, for the left hand side we only have the h of r of interest, and to the right hand side this is just the integral from 0 pressure to the pressure of interest. We did not have any change inside the integral term. So that is just a quick reminder how we get rid of one of the left hand side term. So this is basically the equation of residual property of entropy. How about this entropy? Let's take a look at the entropy. Okay. So I believe this is the answer for the entropy equation, but let's try to follow the analysis we had over here. So in order to calculate the entropy term, so we try to bring in the fact that is the isothermal process. So we would do the same ds of r over dp at fixed temperature. We try to evaluate what's going on. So here we are going to have the ds over dp at fixed temperature, right? dp, we are going to have minus ds star. Remember, this is ideal gas behavior. We have dp, keeping temperature fixed, dp. Okay. So if we take a look at the turn ds, so that is the turn of ds, and we are having dt goes 0. So we are going to use the modified general entropy calculation for derivative into this ds is now this term goes 0 for both the real gas and the imaginary ideal gas behavior at Tp. So this goes 0, then ds is negative dv over dt p dp, right? So this is a modified term for the isothermal process, and that shall be a general equation for that. So now if we are interested in this ds over dp term, then of course we can manipulate this as ds over dp would be, we divide on both sides by dp, so that would be negative dv over dt p. So for the first term, for the first term over here, we cannot do anything, cannot further simplify. So we just write down this is negative dv over dt p dp. Are you still here with me?
Yeah, just trying to understand.
Okay, okay. And then for the second term, this is minus. The second term is from the ideal gas. For the ideal gas, start with this equation. For the ideal gas, we have PV is RT, right? So if PV is RT, then let's try to take a look at what do we have for the dV over dt P minus. So now the volume over here, we can replace the volume by RT over P, right? So that's still dt, that's still the condition of P, there's still a negative sign in front. And now you can see that the R is a constant, P is also a constant. So we can take the constants out of the partial derivative sign. So we have minus R over P. We try to put then out of the partial derivative sign, we have dt over dt at fixed pressure. And that term is 1. Right? dt and dt, they are identical, they are the same. So this eventually for the ideal gas would be minus R over P. Okay. So now if we have this minus, I think this is not necessary, but we need to have this sign. So we know that this whole term for the ideal gas, we simplify this as minus R over P. So this is R over P dP. Okay. So now if you reorganize, we have dP and dP, so we can combine the right. So this is why now you take the derivative from 0 to P, you are going to have SR of P minus SR of P goes 0, and that term is 0. So this is why we are going to have this equation. Took me some time, but we are chemical engineers. We should feel happy with those maths. And we need to see that thermal is a solid science. It's not out of imagination. We are able to derive all those equations. So in the end of the day, you are probably just interested in the equation itself over here. But I hope that you can somehow try to understand the reasoning behind those equations. So that was probably a little bit too much for the early morning. But I hope that by now we are able to claim that we have the equation. For the homework for the exam, there's no need to derive. I'm not going to ask you to derive those equations. This will kill you. Then we need to realize that would be the two equations. And as I explained, if you take a look at G of R, one way to quickly evaluate G of R is G is H minus Ts. This is simply HR over TSR. So there's no need to derive a separate equation to evaluate G of R. But see the textbook. The textbook had a different route of discussion and listed the G of R in terms of G of R over RT. Okay, so try to pay some attention of the residual Gibbs energy calculation. And also in the textbook, there are two subsections about the residual property calculation. Please feel comfortable with those calculations. And I want to quickly show you how we can change from the H of R using the general PVT. Now we are moving to the Z. I hope you still remember Z as the compressibility factor. Z is PV over RT, and for that equation we do not require ideal gas, so any real gas shall be described by this compressibility factor of this one. So how do we move from this PVT to the Z terms? So I was showing you some additional math over here. I promise you this is the last piece of math for this lecture. So we have PV is ZRT. So I hope you can see that now here Z, keep it in mind, Z is a function of temperature and pressure, right? So now the purpose is we try to get rid of this term. We try to replace this dv. That would be the only partial derivative term over there, dv over dt. So if we try to look at dv over dt, then we replace the volume by dzrt over p over dt. Okay, r and p is fixed value, r is a constant, so we take r over t outside of the partial derivative, then this is partial derivative of zt product over t, and z is depending on the temperature as well. So this is like if you have fx multiplied by gx dx, then you are going to have fx times gx dx plus gx partial derivative of fx over x. This very similar idea. So this is why we take a look at the partial derivative with respect to temperature firstly, then this is simply zr over p. And then on the other side, we try to take a look at the partial derivative with respect to z. Now we can put the temperature outside of the partial derivative, so we have RT over P, dz, and over dt. And then to replace the dv over dt term by the newly derived equation, then we should be able to have the two working equations. All right. So that should be the complete discussion of the residual property, which will be a quite critical part for the second exam. So you should feel comfortable in the calculation of residual property, whether it's enthalpy, entropy, or the Gibbs energy. So that is another slide moving forward. Now we still have to evaluate either dv over dt term or dz over this dt term. So we need to come up with equation of state or some correlation to further simplify, further replace those partial derivative terms. So this is why we need to have access to the PVT data. We need to have some equation of state or corresponding state principle, corresponding state theory. So now we are looking at this slide, we are actually moving back to the first unit where we need to evaluate those equations like PVT term, how we are going to solve for volume as a function of others. So that is how thermal is connected throughout the whole semester by those equation of states and those PVT data presentations we're going to discuss today later. So here again is just the review of the diagram, how we come up with the residual property idea and how we are going to reorganize those terms. So I hope you can see that one way to derive the HR is we try to write down the HR as H minus H star, and then we go all the way through the mass to receive the working function. The other way is we could have this HR as a difference of those previous terms, right? We've derived the general term of H. We're able to calculate quite easily of H that if you push this to the zero pressure, that term is zero. That is minus delta H. This is the isobaric process for the ideal gas. So we should have the equation very easily for this delta HP naught, and for the delta HT, This is the also ideal gas behavior for the isothermal process. So one other way to have the H of R is we try to look at H is delta H turn, is delta HT turn. And H of R shall be the difference between, again, very likely this would be the zero term, minus delta HT. And that is the other way we could calculate the residual property. So there are two different ways. One is try to use the derived equation from the previous slides and run the calculation. The other is we are going to look at the initial and final and the two ideal gas processes in between and figure out the difference. And that is more easily performed with the help of the appendix, as we discussed in the example problem. So that the next slide is a summary of what I tried to show you. So if we are interested in the HR term, we should be able to figure out all the 4 terms in order to receive the change. Okay. As I have.
Sorry, I'm confused. How would you figure out the H, the simple H, the first H?
See, that is much
Yeah.
easier. That is much easier than you had expected. Just read the table. For example,
Oh, okay.
if this is a steam, then you just read using the temperature and pressure. You shall receive the H, volume, G, A, what else? Internal energy, so on, all from the steam table or any reference database. So does that make sense?
Yes, thank you.
Mm-hmm. For this term, we try to push really hard to 0. Then all those values would be 0. For the next two, we have to design 2 ideal gas processes, right? One is isobaric at fixed pressure. One is isothermal at fixed temperature. So that 2 terms shall be also easy to calculate. Then you combine the 4 different values to finally receive the residual property.
So how do we know when to use equations of state or the CST parameters?
Well, depending on the problem statement.
Will you say use this equation, or do we have to like decipher what you're saying?
Yeah, you have to decide. So basically, I'm telling you, you have 2 different ways to calculate H of R, right? One is you just go ahead, use H of R, the integral with respect to pressure. You have that equation, right? This is the first way.
Yes, and in that you have to use the PVT data, or would you have to use the equation of state?
Along that way, it would be more easier or making more sense if you are having the equation of state instead of the data.
Okay.
The second route would be try to use H of R is the difference between H minus H. So along that way, it would be much easier if you are able to read all those values. Say, this is H, as you just asked. So if we are having those individual data at the initial all the way to the final TP, but we don't have a quite obvious equation of state, then we use this method. So in the textbook, we shall have examples for both methods. One is to simply read the steam table and get the values at the final state and try to evaluate the change of two ideal gas processes and eventually figure out the H of R. The other is try to use the correlation, whether this is a cubic equation of state or variable equation of state.
Thank you.
Yep. So this is nothing special. This is just to show you the logical flow of those calculations. Not going to repeat that. And please pay attention to this problem. Okay. So that is a quite classical problem for the steam table reading. And that is the other method, not using not this method, but the other method of reading the initial and final states and figure out the calculation. How many of you have carefully studied this example? No one?
I could probably study it a little more carefully.
Mm-hmm. But I'm glad you actually did. How about others?
Yeah.
Good. So we have two out of 66 students.
3.
3,
4.
4. Okay, only 4. Then we will be in trouble again in this coming exam too. So there are a few things I want to remind you, and you probably also had the question while reading the solution. So this part should be straightforward, no trouble. So we are interested in this temperature and pressure. This is our final TP, right? So we are able to read the actual volume, read the actual enthalpy, read the actual entropy. And then we try to calculate the residue. Then we need to somehow figure out when we are going to assume the ideal gas behavior. This is ideal. We need to look at the difference between the two. This is the real. But using the steam table, we could assume many ideal gas states. So which one would be the best state to use? Here is the best state. This is because P1 kPa is the lowest pressure reported in the steam table. So that should be my best assumption over the steam table to have the ideal gas behavior. So this is the explanation you probably need to have why you pick up this specific state, specific pressure instead of others. Ideally, there's no problem if you want to pick up this as 10 kPa. It's still relatively small, right? It's still quite close to our discussion. I told you that if the pressure is generally below 10 bar, then we could assume ideal gas behavior even at that pressure. But if you try to compare which one is better, then definitely this would be your choice because it's the lowest pressure reported in the steam table. So that is the first thing I want to explain. I want to add to the solution. And of course, you need to pay some attention whether this is molar based or this is the mass based. You are going to need that unit conversion later on to figure out the absolute change of the energy. And if you pick up that P naught and T, because we need to have the low pressure to assume the ideal gas behavior. And now if you look up P naught and T is the same temperature of 225 degrees C. Then you can also look up the enthalpy and entropy. So over there, when we are going to have the ideal gas, we are involving this P naught turn to T. But we need to evaluate the ideal gas behavior at T and P, so we can take the difference between the imaginary state to the real gas value we are able to read. So over there, we need to design and calculate the ideal gas property change from P naught to P, keeping the temperature same. So over there, this delta H would be 0, but delta S is not. For the ideal gas, the enthalpy is only depending on temperature, not pressure. But entropy will make a contribution, even for the ideal gas to ideal gas, changing the pressure over there. So we are able to read the true ideal gas, or the best ideal gas we can come up with from the steam table is 1 kPa. This is still the same temperature. So we have the exact value over here. We need to calculate what would be the value change moving to this ideal gas. And then we have read all the values for the real gas. So take the difference shall be the answer. So I think this part will be requiring some calculation. And that is what I have on the slide. I was trying to show you, this is the final, this is the real. You just identify the pressure, identify the temperature, read in the value you have. And then on the other side, this is the best I can do. This is the lowest pressure I have. And if there is an exam, I will also demand you use this state instead of the others. Okay, so you have to pick up the best ideal gas you have out of the steam table or other resources. Then this is the temperature of interest. We read in those values. And I have to evaluate the change of ideal gas by increasing the pressure, so that you can see that I'm going to make a small contribution, changing from 1 kPa to this 1600 kPa. But for the enthalpy, the ideal gas enthalpy does not depend on pressure. So when you are changing from 1 kPa to 1600 kPa, the enthalpy value should be exactly the same. You can double check the steam table to see if this is correct or not. So once you get all those values, then the calculation of H of R, S of R should be straightforward. The volume V of R is the easiest. You read the volume, this is the final state. We firstly read from the steam table. This is to assume ideal gas behavior. We use PV over nRT because the steam table has a unit of per gram. Those values were reported as per gram data. So this is why we need to have this n. Okay. So that would be the first part of residual property. Then for the second part, it's basically a revisit to the previous section. We need to look at the water, the omega TC PC value. Then we follow the standard calculation to figure out the Z value. All right. So this is using the equation of state or corresponding state principle to calculate Z. On the other side, Z is always defined as PV over RT. With the steam table data, we have to modify this as PV over nRT. So P and T would be the condition of request. volume, we read the steam table, receive the volume. R is a constant, N is related with the volume unit. So we are able to calculate after reading the steam table what would be the compressibility factor from the steam table. So this is why we are also able to calculate the compressibility factor from the steam table. And you try to compare that with the corresponding state principal prediction. So this is one of my favorite thermal problems of this unit. You have to show very clear understanding of almost everything. Okay. So at least we have 6 students who have studied, and others I trust you will be studying this type of problems over this weekend. So I'm planning to use the next following 10 minutes to take a further look at the thermodynamics table. So in terms of the data, so that is the example of data we have, and we also utilized the Z1, Z0 table. We have a big appendix on those values. And we also have the TC, PC, omega value. We also have these CP coefficients, right? If you think about the specific heat, we have those A, B, C, D coefficients. So all those would be very useful thermodynamic data available to us, so we can run the calculation immediately. And there are other types of diagrams and tables available to us or from the literature. So I want to have a quick introduction on those. For example, sometimes people are putting together not only a PVT, but try to include entropy and enthalpy. So that is much preferred, because now we, instead of calculating or designing the path for the calculation, we can simply read the table to receive the entropy and enthalpy values at specific PVT conditions. So there are a few common plots available to us. The first one is the temperature versus entropy, and we also have the normal log pressure versus enthalpy, and we also have this so-called molar diagram where we are going to have the H enthalpy versus entropy. We will see some examples in a minute. And in those diagrams, I have a note over here. You need to pay attention whether we are reading the pure gas region or we are really reading the gas liquid mixtures. So I hope you still somehow recall that the PV diagram, we are going to have this kind of curve. Then to this left, we are going to have what? We are going to have pure liquid, right? Outside of this curve, we are going to have pure gas. And then in between, we are going to have these liquid vapor mixtures, right? So that is something you need to pay attention when you are reading those diagrams or the plots. So I had some snapshots from the textbook to show you the general shape of the curve. Of course, first of all, you need to pay attention to the unit, which one is the temperature, which one is the entropy. On this slide, this TS diagram, and which region would be the pure liquid, which region would be the vapor. If you are dealing with the superheated steam, then of course you are trying to figure out some value over the vapor region. If you are looking at the super cooled liquid, then it would be somewhere over here. If you are dealing with the mixture, then you probably have to check those mixture regions. So pay attention to those. And then if this is the log pressure versus the entropy, then again, pay attention, this is the log pressure. If you have this pressure at 10 bar, you need to convert that into natural log 10 and try to identify the corresponding value on the curve. And that is the unit, and again, you need to identify where is the liquid, where is the vapor, so on. And I also have some illustration when you are going to see those dotted lines, then some would represent the constant entropy value, some would represent the constant constant volume, and some would represent the constant temperature, for example, over there, right? And when you try to look at the vapor and liquid ratio, keep in mind that we have this level rule to help us to calculate. And then in the figures, normally they are much easy. We just read those values. So those curves would represent the different liquid vapor ratio. Okay. So this is the temperature, entropy, pressure, entropy diagram. I've explained that already. Pay attention to this constant ratio of vapor and liquid. So here is one other equation I want to have. Sometimes people are putting together this as the specific saturation pressure for a pure substance. So I put down this equation over here. This is the Clausius-Clapeyron equation. I'm not planning to derive, but I include the supporting reading material later in this lecture set. So try to read and try to understand how we are able to move from the fourth derivative from the definition of entropy, and we are able to derive the Clausius-Clapeyron equation. So this again is one other clean demonstration of the log pressure and entropy diagram. So pay some attention to those constant lines, whether it's temperature with respect to temperature, whether it's respect to the ratio of the liquid and vapor. So this will be the general idea of the entropy and entropy term. I found a diagram of, I believe, ammonia, but the diagram itself is providing too much information. So it's better to somehow generate some idea what kind of diagram we are expecting to have. So this is why I think it would be helpful to figure out how the diagram looks like. So the entropy and entropy, we are going to have some constant term for those curves. When you are moving around those curves, those are suggesting the composition would be the same between the liquid and vapor, and you need to pay some attention to the constant pressure or constant temperature term. So if the problem statement shows the pressure and temperature of interest, you need to identify that two lines and have the right reading. So I'll show 2 or 3 examples in a minute or two. But before that, I also want to make sure that we are having lots of tables. So instead of the diagram, we are having lots of tables. And then the steam table would be the most useful. And if you cannot have the required temperature and pressure from the steam table, then you need to run some interpolation in order to have a better estimation of the value at a specific temperature and the pressure. And then once we have those, then combined with the heat capacity, basically we can solve all sorts of thermal calculations in terms of work and heat calculation. So that is the basic information from this slide 24. So basically we have those diagrams, we have tables together with the specific heat coefficients, we shall be able to calculate lots of interesting properties. So I have a quick example over here. So it says the state of 1 pound of steam is changing from saturated vapor at 20 Pascal to superheated vapor at this temperature and pressure. Pay attention, this is the saturated vapor. When you are reading the saturation table, we have two tables. One is saturation, one is the superheated, SU. So try to identify which table you are reading. So here you have to read two tables to receive the data. And it was asking what is the enthalpy and entropy change of this steam. So we know TP. We know the initial is saturation. We know final is the superheated. So here, as long as you identify the correct two steam tables at the required temperature and pressure, there is nothing special. We don't need to design the path, have the integration. We just read in the value and take their difference. So again, this is the superheated steam table, not the saturated steam table. So read the table, then you are going to have the value over there, then their difference should be the answer. Okay. Saturation vapor. Okay. All the way above, you're going to have superheated. So this is a question I had in the past year for the exam. So I was asking students to write down the, I provided the PV diagram to write down the TS diagram. That was a quite interesting question to have. I hope you are also happy with the analysis. So we put together the 1, 2, 3, and 4. We just need to understand what kind of path we are looking at. So this is the isothermal process, right? So dt would be 0. So if the dt is 0, then the entropy change would be 0. So this is why you're going to have the fixed no, this is adiabatic. Q reversible is 0. Then the delta S, the entropy change would be 0. This is the isothermal. You are still going to have the entropy change due to PV change. So this is why from 1 to 4, 2 to 3, you are going to have the fixed entropy. And then when you are moving from 1 to 2, you are going to have the energy import, and the energy will drive the system into a more disordered state. So this is why moving from 1 to 2, the entropy will be changing, will be increasing. Moving from 3 to 4, that will be a decreasing change. So if you understand the Carnot cycle, the essential assumptions behind the 4 units, then you should be able to receive the TS diagram for a Carnot cycle. So this is just a quick form problem to test your really deep understanding of the Carnot cycle. So this again is the way to illustrate those lines for the fixed composition, fixed temperature, fixed pressure, or fixed volume diagram. So here comes the diagram, and This is indeed the reason why I think the previous cartoon illustrations would be helpful for the reading. So if we try to take a look at this, this is a water diagram. So that is produced as the pressure. This is the enthalpy. And pay attention to the unit. This is not log H. This is just a P and H. And over here, we are able to identify. So the most important curve would be the saturated liquid, the saturated vapor. And you can see that in between this curve should be the mixtures. Here we are going to have the pure liquid. Over there we are going to have pure vapor or superheated vapor, right? So when you look at the other terms, you're going to have, for example, this path is a fixed temperature path, right? So following all the curve. And you are going to have this path is the fixed composition path. So when you are reading the fixed composition along different temperature or pressure, you have to move along this curve. And what is this purple color? What is this purple color? Purple color is this density. Or in a way, this is a volume, right? So those would be the curves, or this might be easier to have. This would be the fixed volume or fixed density curve. And then we have one other color over here. This is the entropy. We shall take some pain in order to calculate the entropy, but using the diagram, we shall be able to have those fixed entropy curves, right? Or those would be the mixture. So that value is the entropy of the mixture. Okay, so you can see that we have this P, H, S, rho, T, what else, X, from one single diagram. Again, this is the molar diagram. This is the so-called HS diagram. Pay attention to the unit. Where is the entropy? Yeah. Well, this is entropy. We have to check on the unit because for some reason it does not show up on this diagram. And over here, we shall be able to read all those values from the diagram. You just need to be careful, pay close attention. And again, this is a curve to identify the liquid and the vapor region when we are going to have pure liquid, pure vapor, or liquid vapor mixture over here. Okay, so that's the end of today's lecture. I have some supporting materials to show you how we are able to derive the Clausius-Clapeyron equation. So I'll leave those readings to you. So I have quite lots of chat this time. I'll double check after the lecture, but that's the end of today's lecture. If you have any other questions, stay for a few more minutes. Otherwise, class is dismissed.
Are you gonna post old exams like you did for exam 1 for us to study?
Yes, with the solution. So I shall have those out this afternoon.
Will you be posting the lecture also?
What do you mean lecture?
The recorded lecture for 7, 8, 9, and 10. I saw your email say that you would, but I didn't see it on Canvas.
Oh yes, Mark, he reminded me last night that he could not have access to that. I emailed OUIT to figure out what's going on, but at the same time, I'm going to upload those videos to my research group website. So I'll share the link so that you don't have to wait until OUIT fixed this technical issue. So I'll share the link where you could download those 4 lecture videos.
Thank you.
You might lose one of those videos, like lecture 8.
Lecture
Okay.
9, I believe.
Lecture 9. Okay.
Hmm.
That's close.
Yep.
Yeah, I feel good.
Okay.